Hello, I'm Tad Utreexo. I'm going to talk about Bitcoin nodes, decoupling trust and storage with Utreexo. So quick intro, I'm Tad Utreexo. I work on Bitcoin at the MIT Digital Currency Initiative. Previous work I've done is co-authored the Lightning Network paper, discrete law contracts, and currently working on Utreexo. So quick outline of what I'm going to talk about. I'm going to talk about what is a node, what are these things called nodes in Bitcoin and how they work. I'm going to talk about the history of Bitcoin, Bitcoin history, state, and verification, how those fit together. Verifying the state of Bitcoin with minimal trusted data. And then Utreexo and their design and properties. So nodes, what's a node? Well, from Latin, nodus, not. I don't know if that really applies, but in graph theory, it's sort of the dots that are connected by the lines, right? These things in the middle. And in Bitcoin and similar networks, these are the endpoints. These are the computers running Bitcoin. What does a node do? Well, mainly sends and receives transactions. And the hope is that everyone agrees on who owns what, right? So you send these transactions to move coins around, and ideally, when it works, everyone agrees on who owns what. So how do you do this? Well, there's a bunch of things that nodes do specifically. They propagate messages, send coins, serve blocks, check proof of work, check transactions, receive coins, and mine. And I sort of sorted these in the easiest to hardest. So propagating messages is really easy from a computer science point of view. You don't have to actually have much memory or storage. You don't need to know what a signature is. People just send you messages and you sort of send them around to people. In practice, it's more complex, but you don't need to actually validate. Sending coins is actually easy. So if you have the information needed to send a Bitcoin, signing is very quick. You don't actually need to know much about the system to sign and broadcast a transaction. Serving blocks. So if you're a full node and you give blocks, an archive node to give blocks to other people, again, it's actually really easy. You don't have to verify anything. When people request a block, you request it by hash, you could just send the block out and have no idea what it means. So it's sort of like being a web server at that point. Checking the work to see if a block has the valid proof of work. A little more complex, but computationally quite quick. And then you get to the hard part, right? Checking transactions and signatures in order to receive a coin, or whether the only difference between checking the transaction and receiving the coin is who ends up being the beneficiary, but you got to check them all anyway. And then mining is sort of on top of, once you've checked all the transactions, you can mine. So verifying transactions is the hard part. People are sending coins. And are these transactions okay? So you need to know so many things about these, so much data goes behind whether a transaction is valid or not. A transaction in isolation, you can't tell, right? Because do these coins exist at the right places? And there are enough of them. And what are the keys? And are the signatures okay? And there's so many different verification checks. Script opcodes, interpreter, clean stack, so many things. Just looking at a transaction can be very small. It can be 200-300 bytes. Looking at it in isolation, you don't know if it's valid. You need, in practice today, you have to have gigabytes and gigabytes of space to verify what a single transaction's validity is. And this gets to sort of state versus history, right? So the blockchain itself is history. But you only need the blockchain to get to the current state of who owns what. And that's the chain state or UTXO set. So keeping track of the current state is hard. And you can't directly share it with others. So if you say, I've got this current UTXO set, let me give it to you. There's no messages to do that, really. There's no way to export your UTXO set because you can't verify it, right? I know that here's all the list of who owns what. This address has this, this UTXO has this coins, but I can't share that. I have to share the actual blocks, the actual history. So keeping track of the history is easier, right? If you just want to archive the blocks, you don't actually have to compute much. And it's only really done to help others. The only reason you need to store blocks is to give them to other people, to convince them that your current state is the correct one. Can you somehow get someone else to do the hard part, right? We can throw away the history, right? So pruned nodes have been common for many years, where you play through the history and then delete it. Can we do the same thing with the state somehow? So the answer is yes. There's a new node type that I'm working on called Utreexo. I would call it a full node. It fully verifies, but it does not contain the full state of the system. So you verify everything that a full node does, but you don't keep track of the whole state of who owns what. So you can't look up the coins on your disk. You don't have a database at all, really. So instead, the people spending the coins, or when someone's giving you a transaction, they need to prove that those coins exist. It makes spending coins a little harder, but it makes other things quite a bit easier. So the design is, instead of keeping track, right, the ledger of who owns what, which is built by the blockchain of who sent what where, instead of keeping track of this whole ledger, you really only have to keep track of your own coins and a proof that they exist. And then you sort of keep a hash of everything else, right? So all the 70 million other UTXOs in Bitcoin, UTXOs are sort of where Bitcoins live, the unspent transaction outputs. You just keep this hash of that, and it's very small. And then when people want to send coins, they prove that their coins exist by giving you a proof that their coins are in this hash that you've already gotten verified. So we use an accumulator, which is basically a cryptographic construction where you can sort of throw data into it. You can't get the data you throw in back out, but you can prove that you threw something into it. So it's sort of this, imagine this bottomless box, and you can throw as much data as you want into it. You can never get any, throw as many pictures, PDFs, images, throw whatever you want into this thing. But unlike a hard drive, you can't pull out. You can't get any of the data back out, but you can prove that things have been thrown in. And in this case, we also need to be able to delete things, right? We don't want to be able to double spend or spend the same UTXO twice. So when you verify that something is in this accumulator, you also want to remove it at the same time, which is nice. The only time you need to delete things in Bitcoin is when you're proving them and vice versa. So I'll go briefly into the actual design of how this accumulator works. It's quite simple. It's basically a bunch of Merkle trees, and they sort of move around in an interesting way. And these nodes, these Utreexo nodes, they only need to store the roots of these Merkle trees. Okay, so let's say you want to add items to this accumulator. So in a normal Merkle tree, if you only know the root, you can't actually add a new node and recompute the root, right? Because you don't even know how many things there are. If maybe there's 100 things in here and you want to add one, well, it's not clear to do that. So what you do is instead have a forest of perfect trees. I'll show you this. Okay, so let's say you have a forest, a single tree with 4 leaves, and then you have got one root there. You only need to know the root. Let's say you want to add a leaf. Okay, so now there's 5 elements. You actually have to keep 2 roots now. So you keep one that has 4 in it and one that has a single 1 in it. Let's say you add it again. Now you have 6 elements. These new 2 on their own level can form their own tree. So again, you have 2 roots to represent 6 elements. Now you add, again, you're at 7, you have 3 roots. One that has 4, one that has 2, one that has 1. Powers of 2. And then you add 8, and now you can combine these things. So when you're in this situation, you only know these sort of orange ones. But knowing just these orange ones, you can combine them, right? You can combine these 2 to get that, combine those 2 to get that, and combine that to get the top. Now you've got 8. And now you're back down to a single root that you need to keep track of. So you can sort of see at a glance, you're going to store log 2, right? I'm sorry, log base 2. So log number of elements. In practice, it's log base 2 over 2 because sometimes you don't have to store. So that's adding elements, and that's not that complex, and it's been discussed in other papers. Okay. However, adding is not too bad, but you add sort of on the right, and then you sort of batch things together and bind things together as necessary as you can. Whenever things are sort of on the same row, you say, okay, I know these 2 things on the same row, add them, hash them together in a standard Merkle tree construction, and then you're going to have, log n over 2 roots. Deleting is a little more tricky. Sorry, maybe a lot more tricky. What's interesting though is that if you sort of combine deletion and proving, it works really well. And in Bitcoin, it's great because the case is you only need to delete things as soon as they've been proven and vice versa, right? When you're proving that a coin exists. The only reason you need to prove it exists is so you can delete it. So I'll show the sort of intuition. You've got these. So here's an example where you had 7 elements, right, and 3 roots. And you say, okay, I want to delete element 2. The proof for element 2 is going to be 3 and 8, right? It's a standard Merkle proof. So the siblings all the way up to a root. And if you know 3 and 8, you can say, okay, well, I'm deleting 2. I'm going to move 6, right? 6 is this one that's off on its own. 6 moves to where 2 was. And now I recompute. I can recompute 9 because I know 3. 3 was part of the proof. I can recompute 12 because I know 8. 8 was also part of the proof. So now I've got a new 12 where 6 has sort of swapped in for the thing that got deleted. This is great. I know the proof was exactly what I needed to recompute the root with this new substituted element. And similarly, then you discard and you're done. Let's say another example where I have exactly 4 nodes and I want to delete this node number 2. In this case, I don't have anything that can swap in. So it's like, how am I going to do this? Well, the proof is again 3 and 8. In this case, I say, well, nothing's going to take 2's place. However, I do know what 3 is. I'll delete 2. And if you look at it, well, I've got 2 trees now, right? 8 exists. 8 can be its own tree. And 3 exists. 3 is its own tree. So I just delete that, delete that. Cool. Now I've got 2 trees. So the intuition is that you've got these proofs. And if there are basically these 2 cases sort of these 2 examples actually work all the time because you either have an even number of leaves at the bottom or an odd number. In the case where you have an odd number, that odd one swaps in to the thing that got deleted. If you have an even number, the sibling of the even one that was the sibling of the node that was deleted ends up being its own tree. And so it works, and you can batch these deletions together and it's quite efficient. So things sort of delete, and then you always have this log n over 2 number of roots, which ends up being a few hundred bytes, always less than a kilobyte with the current Bitcoin code. Even if you got up to, I think, 4 billion or 8 billion UTXOs, you would never exceed a kilobyte of storage space. So the downsides. So now you got these proofs, right? So you need Merkle proofs for potentially all the inputs. All these UTXOs that are getting spent need to be proven that they exist. And not just that they exist, but what they are, right? How many Bitcoin is there? And what is the pub key script and all the other aspects can go into this hash at the bottom of this accumulator tree. And then the question is, who makes these proofs? Well, the nodes themselves can make it. Or the other issue is, what if you're getting transactions from someone who hasn't upgraded and hasn't used this software? They don't care about it or want to. Well, so you need a bridge node, a node that stores all the proofs and can tack on any proof instantly and push it over to a node that wants these proofs. So that's one of the hard parts of doing this is you need to make a bridge node. Bridge nodes, it works, right? It ends up being a couple gigabytes. You can run it on a regular laptop. It's not too intense. But you do need some of them to sort of provide these proofs for the network. And those proofs can then be propagated peer-to-peer. So you only need a few bridge nodes to support potentially many Utreexo nodes. The other downside is there's more to download. That's the big performance hit here, right? It can be potentially a lot faster because you don't need to do any disk access. All the data you need to verify is right there, but you do have to download more. So in most cases, this is faster, but if you're really bandwidth constrained, it's not. And in the worst case, you can download potentially more than twice as much data. So right now, the Bitcoin blockchain is about 300 gigabytes. This could potentially make it 600, 650. It's a lot. But that's with the naive, with no optimizations. It ends up being that. You can get that much lower, as I'll show. So how do you minimize this extra download overhead? So you can cache the proofs. I won't go into the diagrams, but you can see that you've got these big Merkle trees and elements of them are moving around kind of. Every block, things change, right? Every block, you're deleting a node, you're moving things around. But most of the tree doesn't change, right? Even if you're moving some leaves around, let's say you have right now 70 million UTXOs, you might be deleting a few thousand of them, 3,000 or 4,000 in a single block. So the vast majority are unchanged. And so what you can do is you can cache parts of the tree that don't change. Or really what you're doing is you're remembering parts of the tree that recently changed. Because as you can imagine, things that most recently changed are likely to change again. If you just have a new UTXO, a new output that's just been created in a transaction, it's quite likely it will be deleted and spent very rapidly. In fact, we can do better than like most recently used. A regular caching algorithm will say, okay, well, these things have been created recently. I'm going to keep them in RAM, or not flush them to disk, or in this case, keep them in RAM and not require a proof. But we can do better because the whole blockchain, if you're syncing up the blockchain, it's known beforehand. So the node you're downloading from can sort of give you hints and tell you, here's what to keep in your cache because this is going to get spent next. The whole history is known beforehand, so you can have this optimal caching. You can look into the future. A fun graph that sort of shows the lifetime of these UTXOs. I couldn't put 0 because it's a log scale graph, but 1 here means that this is the number of UTXOs that lived a single block long. So they were created in block n and then spent in block n plus 1. And that is the most popular, or really second most popular. So the most popular was 0. And then 1, 2, 3. Interesting, there's a bump at 6. Many people wait 6 confirmations and then spend their coins, because it was mentioned in the paper. Another bump at 100 because miners have to wait 100 blocks. Another bump at 433 and 1,000, and so on. But you can see, this is the power law kind of distribution where many of the coins, many of the UTXOs live a short amount of time. And then many of them, as it trails off, will live a long time and so aren't getting spent. But this is great. If you see a graph like this, you're like, awesome. This is so, optimizable. If I have a good caching, if I just remember 10 blocks ahead, I get, something like half of all transaction inputs. So, end result, what you can do is the more memory you dedicate to caching these proofs, the less proof you have to download total. So you actually need something like 11 something gigabytes to not need any proofs at all, which is worse than just holding the whole UTXO set. So once you're getting into 6, 8 gigs, the whole point is somewhat lost. But what you can also see is that right in the beginning, you drop real fast. So if you only have a few hundred megabytes of memory to dedicate to caching, you will significantly reduce the number of the amount you need to download. So download overhead, let's see, something like, and this is the look ahead. So the actual way we do it is, look ahead 100 blocks, look ahead 1,000 blocks. This is a bit old data, but the new stuff looks about the same. So the idea is if you can dedicate a few hundred megabytes to memory cache, then your download overhead only ends up being 40 gigabytes, 50 gigabytes, something like that, which is still a lot, but that's alongside the 300 gigabytes of blockchain data you need to download. So in comparison, it's like, oh, this is 15%, not a huge overhead, and gives you the benefit of not needing to store anything at all. You're less than a kilobyte. The other thing is it's not a soft fork or hard fork. If there's no consensus, no problem. So miners don't need to know about this. People might be using this right now. I mean, you can use it on testnet right now. It works. I definitely don't use it on mainnet yet. So you need to start with bridge nodes and archive nodes to keep all these proofs. But it's nice. It's permissionless innovation. You're not going to have any arguments over starting this because people can just use this new software which requires proofs and have bridge nodes to provide these proofs. And whatever transactions they're making, it's really easy to strip out the proof and send it over to the old software, right? The old software will take these new transactions with proofs and just, remove the proof. So what is their build? What can you do with this? Well, the obvious benefit is your full node is now tiny. So instead of taking up a lot of space and having a lot of disk IO, it doesn't. It also leads to a lot of cool things you can do. So when the state size of your system is so small, it'll fit on a QR code. And so you can copy it around easily. You can do a lot of cool things. You could, for example, sync your full node using this on your desktop computer at home. And you trust your desktop computer, it's yours. And then copy that entire state to your cell phone. And instead of having your cell phone work for hours or potentially days and download hundreds of gigabytes, it's just QR code and it transfers the phone. Your phone's now synced up. And this is not you losing any trust. You could potentially do that today, right? You can go into Bitcoin and copy your whole chain state folder from one computer to another, but it's for something gigabytes, and it's not practical to do. It's not really supported. You could also, yeah. So, wrong slide. So you can do that with this much easier. Yeah, there's other things you can do. You can make you split up the validation. So maybe you have a couple computers and you take turns, or like this computer does the first 300,000 blocks, this computer does the next 200,000, this computer does the end, and they can sort of run in parallel and transfer states to each other very easily. Okay, so that's basically the gist of the talk. The idea, maybe you can have full nodes on phones. Like, it does help. You still are using the same amount of CPU and bandwidth, potentially more, but it does solve a lot of the issues. So a good thing to think about this, like a Raspberry Pi plugged into your router. It's perfect for that, right? You're not bandwidth constrained. So an extra 15, 20% bandwidth, no big deal. But a Raspberry Pi is really disk I/O bottlenecked, right? You've got to write to this little micro SD card, and having a database on that is painful. So with this, it stays in RAM, much faster, easy to run on a Raspberry Pi. We currently have code. It's working. You can download it, compile it, try it on testnet. We have weekly calls discussing development of this. So it's up on GitHub. And more open source contribution is definitely welcome, or other questions. So that's the end of this recording, and I will take questions now. Thanks.